Hi, Hannah. Hi, Tristan. Welcome to the podcast.
Thank you.
Thanks.
Let's begin with where you work and what you do, Hannah.
Sure. So I'm Hannah Kerner. I'm an assistant professor at Arizona State University in the School of Computing and Augmented Intelligence. I'm also the AI lead for the NASA Harvest and NASA Acres programs, which are NASA's agriculture and food security programs focused globally and on the US. And I'm also a research advisor for Tailored Geospatial. So my lab at ASU focuses on developing machine learning and AI algorithms, data sets, knowledge, and scientific advances that can support making AI work for real people and delivering on a lot of the challenges that we have in the real world, particularly related to environmental challenges. So we do a lot of work on machine learning for satellite data, including developing systems often that support agricultural monitoring, which we're able to deploy for real users through NASA Acres and NASA Harvest, and now through Tailored Geospatial as well. Um, and work on trying to actually get these research advances into the hands of end users.
Fantastic. How about yourself, Tristan?
Hi, I'm Tristan Grup. I'm an agricultural data scientist at World Resources Institute, which is a global think tank organization that does critical work for people, nature, and climate. I work in WRI's data lab. It's WRI's core innovation and data productive delivery unit. So our mission is to harness data to advance data technology to help communities improve lives, protect nature, and ensure just transitions. I'm also in the Food, Land, and Water program, which tries to address urgent challenges related to food, land, and water security. I'm really excited to chat with you today.
Excellent. Thanks, Tristan. So we're connected over fields of the world. Hannah, maybe you give us a bit of background to fields of the world.
Yeah, so Fields of the World is really, it started as a benchmark data set, but has evolved into a whole ecosystem of tools for supporting field boundary segmentation globally. So that's the idea that we want to take a satellite image and be able to draw a vector polygon representing every field along its boundary, and be able to create solutions that work well anywhere in the world. So Fields of the World has a benchmark data set that we can use for training models and benchmarking progress of new models that are developed using that data set for field boundary segmentation. That includes, I think, 26 countries globally. So we have not just like a single performance over the whole world, but you can get group-wise, country-wise performance, and models are scored based on how well you do on average across these countries, to kind of address the bias that many models have on performing well in data-rich regions. Um, and we also have lots of tools like a CLI for running these models. So you can really easily use our CLI to download, search for images, download satellite images that go into the model, download different model checkpoints that are hosted publicly, and run model inference for new regions. We also have a web app that you can use if you don't want to run the CLI or write any code. The project is entirely open source, so you can go in and see all of our code on GitHub and even make pull requests, assign some issues to yourself if you are interested. It's really an open source community effort to develop the infrastructure that's needed for achieving global field boundary segmentation.
That's fantastic. And I'm curious what state-of-the-art performance looks like on field of the world.
Yeah, that's a good question. State-of-the-art performance looks different in different places, as you might imagine. I don't think anyone listening to this podcast is surprised that models perform differently in different parts of the world. So most of the data that's in fields of the world, most of the data that's publicly available for ground truth field boundaries that we can use to train the model are in larger agricultural systems that have more regular field boundaries or larger fields, which are easier to identify the boundary of in Sentinel-2 data, which is 10 meter per pixel. So in certain places that are in distribution to the model and have fields, even if they're out of distribution to the model, but have fields similar to a lot of what the model has seen, state-of-the-art performance looks really good. It looks generally like if you looked at the boundaries, maybe you see some errors where you're like, maybe I would have drawn a line in between that, or you might have done something slightly differently, but it's pretty much solved, I would say, in a lot of those places. In places where the fields are much smaller, there's more heterogeneous mixed cropping systems, especially when those boundary sizes start to be below the scale of Sentinel-2, that's where we see more challenges. But if you're familiar with this problem, I think of field boundary segmentation and these kinds of resolution issues, still state-of-the-art performance in regions that are totally out of distribution and very small, challenging areas, we get, I think, pretty surprisingly good starting results. And then it's pretty straightforward to improve the model by adding new training data. It's very, very responsive to new training labels in a new region. And that's something Tristan will tell you more about.
Fantastic. Tristan, over to you.
Can you remind me of the question?
Extending to new locations.
Right.
Yeah, so Tristan, I just was thinking that in the effort to improve the model in South America, the results look pretty good in some of these
Right.
regular large scale cropping systems, but to improve it on the mixed systems we see in South America, training data was super helpful.
Yeah, exactly. And I think that's how we approach creating new training data for South America, was trying to capture the diversity of agricultural practices that you see there. I think in the word agriculture, it's agriculture, like culture, a specific culture produces agriculture. It varies around the world. And so capturing diversity and training data was really important for this project. Um, you can see huge diversity in agricultural practices across South America. You see shifting cultivation in the Amazon. You see really vast pasture and soybean fields in northern Chaco, in Mato Grosso. And then in mountains, there are very small snaky fields. And so agriculture varies a lot with the culture that practices them, the ecology that it exists in. And so we approach training data collection with diversity, capturing a bunch of different conditions. The training data set in Fields of the World was this small segment of fields. I think it's 0.11% of the overall FTW training data. So we really wanted to expand it, make Fields of the World work in South America. And so we added a bunch of new labels through targeting this diversity and challenging conditions. And we saw that it really helped the model generalize across a bunch of different contexts. So yeah, diversity of training data was really important for this work.
Right. And did you consult an expert on South American fields, or did you have to become one to identify which areas needed annotation?
Uh, so I've been working on South American agriculture for about 8 years. I started my work in the Peruvian Amazon. They have this really specific style of shifting cultivation that I've been characterizing. And then just generally working on agriculture in South America, you've come across all these different practices, read about them. And so I came in with a certain familiarity with the diversity of practices, but I had to learn a lot as well. And so to really get a sense for all the diversity of practices, we ran the Fields of the World model in South America and saw where the model wasn't performing well. And in those areas, we hand annotated field boundaries. So we look to see, okay, is there a low model performance here? Let's sample here. Let's create an initialization baseline. Let's create a nice base to work from. And we focused on areas of Fields of the World, the Fields of the World model underperformance, and sampling in 17 ecoregions in South America. And so that diversity was our approach. And I had to look at a lot of model output results, make sure that we were capturing a bunch of different systems. So a lot of that was qualitative and getting used to and getting familiar with the different types of agriculture. So I learned so much about the different systems, and that was a really fascinating part of this work.
Hmm. I'm sure some are very kind of niche and localized. So how do you decide when you have covered and captured enough data for, each of these different kind of subclasses?
Uh-huh.
Vibes.
Vibes,
Vibes.
yeah.
I'm done.
No, no. I mean, annotation effort is costly. Even when we have these annotators on our own team, um, you really are careful to not overestimate. So, we try to do what seems like a minimum amount and see how things go and then add more as needed. So, Tristan can tell you more about this, but we essentially started with what we thought seemed like a low, reasonable number, about 50 chips in each ecoregion for this sampling of low performing areas in each ecoregion. And then we also used the updated model to look at where things were performing poorly and also, collect whatever data we could from various partners to add into the model. And I think in the end, that ended up being about 900 chips added to Fields of the World, which is really a small amount compared to the overall data set, which is about 70,000 chips. But even that small amount with no reweighting, just adding them into the model, appending it with the existing training data set has a huge impact on performance in the region.
And you mentioned the model, so there is a single global model, and the objective was to bring that one up rather than create kind of location-specific models.
Yeah, Tristan, maybe you want to share a bit more about the experience of trying to fine tune these models in different places. I think what many people assume in agricultural monitoring or machine learning with satellite data is that specializing local models will typically do better. But I think we find in a lot of cases, and especially in this project, that it's really important to retain the global size of the training data and diversity of the samples that were there. Again, because the cropping systems in South America are so diverse across the entire continent. And so we were, adding some specialized training data, but it's still training on that alone was not as good as training with the global data as well. And you really
Yeah.
want to train in a way that retains that previous knowledge.
Um, just to jump back to this point about training data, we originally thought to do 100 samples in each ecoregion, and I was labeling, and my hands started cramping. I was like, we got to stop it at 50. This is way too much. But that first 50 samples that we did, I think it was actually 83. Then we dropped it down to 50. We did fine tuning in Bolivia, and there's this really particular pattern in the Bolivian Chiquitania with these huge, large strip soy fields and these radial massive fields. And that was our first fine tuning training data set. And when we did fine tuning, we saw model performance drop significantly. So with full fine tuning, it went from the base model in Brazil, so against the Brazil test set being 96% pixel IOU, and it dropped down to 42% even after we added this Chiquitania training data. And so we saw model performance fall. And so that I think that speaks to Hannah's point that you can't just add local data. It's not always going to make a better local model. There's a lot of great knowledge from other contexts. And so the combination is why we decided to go with these fully trained models with the full FTW baseline plus the South America data, because we didn't want to have this issue of catastrophic forgetting or losing really interesting or really valuable data from other contexts, training data from other contexts.
Right.
Yeah,
So then
and part of, sorry, I just add to that, part of what we want to do in adding new training data is specializing to the types of patterns that humans are paying attention to, like the different types of agriculture. But there's a lot that models are paying attention to that are not necessarily relevant. And so having more training data often helps the model become more robust to these things like cloud cover or certain colorations, these subtle things that humans are ignoring because we're well evolved, but models can be quite sensitive too.
Mhm. I'd love to understand a bit more about the process you went through to choose the particular model, because you've obviously got CNNs, transformers. They might have different areas they perform better or worse in. Is that something that you can talk about?
Yeah, so in the first fields of the world kind of sprint that we did with the first paper that we published on this benchmark data set, we basically had the hypothesis that the issue in solving this problem of global field boundary segmentation was not that we didn't have a good enough model architecture, it was that we didn't have enough data. And so we focused that first effort on creating this large scale field boundary segmentation data set that we could use to train any model architecture. And we did very little experimentation on which architectures we experimented with in that first paper, which was published in AAAI last year. And so there we basically said, we know UNets work well for segmentation. We're going to use a UNet. Maybe we'll sweep a few backbones like efficient nets or deep lab just to see how much sensitivity there is. We found that there was not much sensitivity. Most of the sensitivity was coming from the data. So we kind of kept that as just a pretty standard lightweight model and focused on the training data development. Then, after we published that data set, we said, well, how much can we juice out of this benchmark data set with model improvements? So then we started an effort that we called the Bake Off, which, as you know, somebody living in the UK, I think you're probably very familiar with Pru.
Mm-hmm.
So we ended up calling our eventual model Pru, which is some tortured acronym for practical recipe for field boundary segmentation. I'll let you work that one out, how that comes out to Pru. But basically there, we said, okay, let's now keep the data set fixed and try out a whole bunch of different modeling choices. So we tried a whole bunch of different choices within UNets, so changing different weightings on the loss function, changing different loss functions, using different backbones in terms of the backbone architecture, but also the size, like efficient net B3 up to B7, as well as other architectures. We tried other types of models, like treating it as instance segmentation, using models like Mass2Former instead. We also looked at geospatial foundation models, fine-tuning them on the fields of the world data set. We tested like, I think 11 different models on the data set. So it was a really, really big modeling effort. I don't know exactly how many checkpoints we created here. I think it's like over 100 for sure, but really pushing on seeing, what limit we could hit with the modeling now that we had this training data available. And we were able to improve the performance quite a bit by pushing on that and getting, I think, over 10% improvement on the benchmark performance. And again, that what came out of that essentially was a recipe that worked well for doing field boundary segmentation that is not just applicable, really segmentation in general, we're finding when we've tested this on other projects too, but that's something that can be applied for field boundary segmentation in general, not just for the fields of the world data set. And another thing we looked at there was testing these models, not just in terms of benchmark performance, as in, IOU, precision, recall, blah, 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 on the test set, but trying to create additional metrics that would better approximate how the model is performing on new samples out of distribution. Because what we were finding after Fields of the World V1 with the standard UNet we had from that paper was that there were a lot of systematic issues that weren't really captured in the benchmark metrics. This is no surprise to anyone, I'm sure, but so we created a few metrics like one that we called consistency, which is looking at how consistent the predictions are if you slide the window over a little bit to try to get at these edge artifacts that often occur with models. We also ranked models on throughput. So how many kilometers squared per second could be processed as a proxy for cost, which is hugely important for making maps, and some other metrics looking at robustness too, like brightness or orientation kinds of things.
Right. Very interesting because often you can get fixated on the IOU metric or something, but as you say, the end users don't really care. They have some other experience that they want to measure
Hmm.
somehow. Very interesting. Okay, so we moved on. Version one, version two, both model and the data set by the sound of things. What was the kind of performance jump for those South American regions with the version two then?
Yeah, Tristan, do you want to speak to, I think in particular when we integrated some of the models that were developed along the way in this bake-off, some different choices like changing the boundary class weighting and things like this, we saw pretty major improvements in a lot of places.
Yeah, we really did. So I think one of the starkest jumps was that the Fields of the World base model on soy in South America was looking at like 47% pixel IOU. And then after adding new training data, it jumped up to 77%. And that was just the first iteration. Um, Adding new training data on top of that, so we trained 4 different model variants. And the final one included these challenging active learning samples. And that's where we saw the biggest jump up in object recall. Pixel IOU didn't change much, but recall shot up by more than 20%. So we were able to see huge gains by adding just a small amount of training data. And again, like this number of samples, I think it ended up being after active learning about 1,200 new samples, makes up such a small number of the overall FCW training data set. But we see huge gains, especially in object recall. Yeah, so these increasing training data is hugely important for making these models performant.
But on the modeling
Fantastic.
side, some of these elements of the Prue recipe that we applied to the South America mapping, I think, most notably saw improvements in overprediction of the boundary class. So fields of the world models predict boundary, field interior, and background. And we emphasize that boundary class to really make it draw the boundary, not just merge fields together. But the first version model kind of took that too seriously, and we saw just prediction of boundary class everywhere. And so when we actually segment fields from that, when we vectorize fields from those raster predictions, we just keep the field interior class. So that meant that all this stuff that was being predicted as boundary was just missed by the model. Um, and so it also led to a lot of really eroded field boundaries because the boundary class was being predicted so much and there wasn't much interior class being predicted, which is again the part that gets vectorized as the field object.
Mhm.
So the pre-recipe really improved that boundary over prediction issue.
And
Got it.
we actually shared some of these model results. So that first version of the model, which overweighted the boundary, as Hannah was talking about, we produced model results for that version, and then the change in the loss function weighting version, and we shared these boundaries produced from these models with actual users. And one of them was someone from the Federal Finance Institution that invests in sustainable agriculture, and they noticed the difference. So they looked at the version one model with the higher boundary weight, and they said it looked buffered in. But then on a more recent version, I can directly quote from them and say, this data strongly aligns with our expectations. Precision, spatial coherence, and compatibility with national land use data sets make it highly useful for monitoring, planning, and agricultural intelligence. So they also said that the latest version of the model would be great for area-based estimations, again, solved by that boundary class reweighting. So we had users directly give us feedback about these modeling changes, and they saw the improvements and were
Mhm.
excited by them.
It sounds significant that only a small amount of actual annotation had a big impact on the model itself. And we can imagine that in other parts of the world, people might be thinking, can I do the same thing? How, what do you recommend for people that might be thinking that?
I would say probably. So we have a lot of documentation on the GitHub page for how to train these models. But with this project that when WRI is releasing different uh, additional tools that we developed to adapt the model for the South America use case, there's going to be more documentation about how to create new training data and add that data to models for people to improve if it's not working well in their region. So those are resources that people can build on that might help to add more context from the Fields of the World repo. Fields of the World community is also working on tools to help with annotation in new regions, help people add or even edit the boundaries to give feedback and incorporate new updates into the model in the future. So basically, you can do this on your own. And if it's not working well for you right now, that's the first place I would start. Don't be trying to get a geospatial foundation model to fine tune. It's not going to work as well, I promise, as one of these units. And then stay tuned for our next version of the data set that's going to be coming in the next year. I'll say I'm not going to make promises on exactly when in the next year, but I'm really excited for it. It's going to add a lot of new data and have new labeling efforts to fill in the gaps in poor performing places too.
That's really great to hear. I'm really looking forward to hearing what comes in version 3. So just to bring things to a close, so version 2, the paper, the data set are imminently released. Is that right?
Yeah, so the first paper is already released. You can find it, just search Fields of the World archive, or maybe it's linked with this episode. Like I said, that was published in AAAI last year. So that published the data set and really the baseline models. The second paper will be on archive any day now and will be published in the CVPR proceedings this summer. And that has all the results for this big model bake-off and describes the Prue recipe. But the Prue model checkpoint is already available through the FTW ecosystem. And also very exciting, in the next several weeks, we're going to be, I'll say several months. Again, I don't want to overpromise, so I'm super excited. We're going to be releasing a global map of predicted field boundaries to make it even easier for people to get the initial boundaries from Fields of the World.
Fantastic. So people just go to their neighborhood and see how the model performs there and access those boundaries. Wonderful.
Yes.
Well, really interesting project, very impactful. I'm delighted to hear that it's going to keep going and address other areas and so forth. Obviously, sounds like the website for Fields of the World is the main place for people to go to get started.
Yeah, the website is good if you want to get started. We're trying to update that website to make the entry points for different types of interested people more clear. And if you're a developer, want to work on open source projects, then definitely come to our GitHub.
Fantastic. I'll put the links in the show notes. And once again, thank you for joining me today and all the best in version 3.
Thank you.
Thank you.
Right.